And last time we were talking about the equation of conservation of the potential vorticity. Potential vorticity, which is essentially the ratio between the vorticity, the absolute vorticity, and the depth of the ocean. And this, if you do the derivative, total derivative of this potential vorticity, it should be zero following the particle, which what we then mentioned last time, that that means that the particle will be moving along the lines theta plus f divided by h, along the lines of the ratio between the potential vorticity and the total depth of the ocean. Or in the first approximation, usually the theta, the relative vorticity, so that means the vorticity of the fluid is smaller, an order of magnitude at least from the planetary vorticity. Therefore, we usually, very often, we can neglect the theta with respect to f. So we have d dt f over h. So f over h, in that case, f over h has to be constant along the trajectory of a water column. So what means that the water column, or the particle in the ocean, will be moving along the lines of f over h constant. So if the ocean increases the depth, the f has to increase at the same vice versa. If you decrease the depth, the f has to decrease. In other words, that means that if the particle is for some reason has been forced to go into the shallower water, it will turn automatically toward the equator in order to satisfy this equation, d dt f over h is equal to 0, or vice versa. If the particle is moving toward the deeper water, it will automatically go northward toward the area where the planetary vorticity is higher. But usually there is, if we assume that there is no outside force, the particle will not be forced to move across the lines of f over h constant, or the particle will be moving by itself along lines f over h is constant. In an ocean of constant depth, obviously the motion tends to be zonal. Zonal, that means from east to west or from west to east, if the ocean depth is constant. So we will be now looking at this zero here, because this zero, and behind this zero, there is a force which there is an external forcing which should force the particle to move across the f over h, move across the f over h lines, and and this is what I mentioned this example before last time. That when the particle arrives to the subsea ridge, this is a ridge, the particle will not be, if not force, if it's going by inertial, as an inertial motion, it will not go across the ridge. It will move in such a way that it will turn equatorward to conserve the potential vorticity. Because here, in this part here, f over h is to be constant. H is smaller, and therefore f has to be smaller in the case of the flow over the ridge. Therefore, in order to keep the f over h constant, the particle will go around around this ridge, leaving toward the equatorward. Okay, so that's an example how the flow, in this case is barotropic flow. Why we do talking about barotropic flow? Because the entire water column has a constant density, and so if you squeeze the water column, the water column will gain will be F will be gaining the negative vorticity, and therefore it should go equatorward, and vice versa. If you have this type of pattern of the bottom, then the particle will be moving northward of this thing. Anyhow, and here is the how do we produce the relative vorticity? The relative vorticity, that means the vorticity of the particle. There should be a force, as I told you, which makes the water column moves from the shallower water, for example, to deeper water, or vice versa, from a deeper water to shallower water. And from the equation, what we have seen here, there is no force for such thing. We will be now talking about this force, which may make the particle going between shallower water to deeper, or vice versa. What is happening if if the water column is moving from the shallower water to deeper water? Moving from the shallower water, from the deeper water, the relative vorticity of this particle is increasing. Why? Because you are stretching you are squeezing reducing the radius of this water column, and due to the reduction of the radius of the water column, the particle starts to move faster. By moving faster, so that it gains the vorticity and reduces the moment of inertia of the water column, causing it to spin faster. So the water column was spin faster here than there. By moving the water column from here to there, you create the potential vorticity, the relative vorticity of the water column, and it spins faster, or vice versa. Obviously, if you move the water column here from this depth here to there, the water column will be moving slower, will be rotating slower, and will be losing the relative vorticity. Okay, as we have seen from the equation up, there are, for the moment, we don't have any force which makes this particle going from deeper to higher, from lower depth to higher depth, and vice versa. And now we will be talking on what is the potential force which makes the water particle moving from deeper water to shallower water. In this case here, if the particle is moving along the lines of equal depth, this is the inertial motion. So that means there are no forces on the right-hand side of the equation. Now we will be seeing what forces can produce such a movement of water particle and produce the relative vorticity of the water particle. So we will be now talking about the response of the upper ocean to winds. This is one of the forces which are acting. As you remember, at the very beginning of our course, we were mentioning what are external forces which are acting on the ocean. One of these are the wind. So the wind, the wind is a mechanical forcing which makes the moves the upper layer of the water column, upper 1,000-meter layer of the water column, due to the difference in velocity between the air and the water. Typically, the wind speed, you may know that the wind speed is on the order of 10 meters per second. Okay. While the typical current speed in the ocean is 10 centimeters per second. So we are talking about the two orders of magnitude smaller velocities in the ocean within the velocities different in the ocean with respect to the atmosphere. Therefore, the air above the ocean typically moves 2 orders of magnitude faster than the ocean, and this is how the ocean, through mechanical forcing, acts on the sea surface through the friction between the air and the atmosphere, between between the atmosphere and the ocean. The atmosphere makes the surface layer of the ocean moving. As I told you before, we typically talking about the impact of the wind is felt at the first 1,000 meters of the ocean. So if you consider that you have ocean typically 5,000 meters deep, there are still now another 4,000 meters of the ocean whose motion doesn't depend directly on the wind. There are other forces which are acting on that part, but the wind is not important below 1,000 meters. Let's see what are the important concepts of the response to winds. First of all, the changes in the wind stress produce transient oscillations in the ocean, which we call inertial currents. Inertial currents, you remember we talked about the inertial currents at the very beginning, which are associated to a certain extent somehow to the wind. Why? Although the inertial oscillations are obtained as free oscillations, they are associated to the wind because the wind is variable. If the wind is variable, or if the wind suddenly stops, the inertial oscillation starts to be produced. And they are produced due to the fact that there are at the very moment when they are produced, at the very moment there are no forcing. So that is why they call inertial oscillations, inertial currents. And so, but they are still associated with the wind because they are associated with the wind which has been blown before they are generated. And here we have seen also that the period of the currents is 2 pi over f, where f is, as you remember, Coriolis parameter. So in our latitude, the period of inertial oscillations is on the order of 17 hours. So this is one of the aspects of the response of the ocean to unsteady wind, to the wind which changes with time. On the other hand, we have the response of the ocean to steady wind, which are more important. The response to steady wind is more important, obviously, than the inertial currents. Inertial currents are very limited in time and space, so they don't contribute too much on the redistribution of water masses in the ocean. Steady winds, on the other hand, are important in the sense that they are creating the long-term, large-scale motion in the ocean, which are changing very slowly, and therefore have an important influence on the redistribution of water masses in the ocean. And the similar thing as thermohaline circulation, the circulation due to the differences in temperature and salinity between different parts of the ocean. These are very slow motions on the order of 10 centimeters per second, which are then bringing or taking with it different characteristics of temperature and salinity, and they are redistributing the heat and salt over the world ocean. As I mentioned before, this influence of the wind is limited to the upper layer, to the sea surface layer, And there are three important things which we should remember, and then we will see from the equations that this is these characteristics are obtained from the equations. First of all is the direction of the wind-induced current. Wind-induced current is at the very surface is 45 degrees to the right of the wind looking downwind in the northern hemisphere. So if you have the wind blowing, for example, from north to south, to north to the south, in the northern hemisphere, the wind is generated by this current, by this, the current generated by this wind is not downwind, but it's right 45 degrees to the right of the wind looking downwind. So therefore, to the right-hand side with respect to the wind direction. As far as the speed is concerned, the surface current speed is 1 or 2% of the wind speed, and depending obviously on latitude. So we are talking, as I told you before, of the currents which are 10 to the minus 2 orders of magnitude smaller than the wind speed. The direct influence or the solution you will see later in a minute. You will see that the solution of the wind of the equation which approximates the influence of the steady wind is felt from approximately from 40 to 300 meters, depending on latitude and wind velocity. So as I told you before, it was about up per 1,000 meters. So, but this direct influence, which has been obtained by applying the equation and getting the solution, is only 40 to 300 meters. Another thing is, another concept is that careful measurements of currents near the sea surface shows that inertial oscillations are the largest component of the current in the mixed layer. That's one thing. That's we said that the more important part of the wind-induced currents are those steady flow. But as far as the magnitude is concerned, as far as how big are those currents, the inertial oscillations are the largest component. They go up to 1 meter per second. So inertial oscillations are up to 1 meter per second. So they are very large magnitude, but they are less important from the general large-scale situation in the ocean. The flow of inertial oscillations is nearly independent of depth within the mixed layer. Mixed layer is the part, you remember, this part where the density is practically constant from surface to a certain depth, so to a certain layer, where the wind is mixing the properties of the water. And so you have the vertically constant distribution of temperature, salinity, and density. At the inertial period. So you have these inertial oscillations are oscillations with the 17 hours more or less at our latitudes. They are moving at 17 period on a period of 17 hours, but this applies to entire surface mixed layer, which then goes back this way. So it makes turns, and within the 17 hours makes the whole turn. The Ekman layer, which is the layer where we feel the influence of the wind, of a steady wind, which is 40 to 300 meters, depending on latitude and wind velocity, exists not only in the ocean, but exists also in the atmosphere, because in both ocean and the atmosphere there is a friction which influences the velocity field. The same thing as in the ocean with respect to the atmosphere. The atmosphere starts to dragging the surface water with it at the surface in the atmosphere, in the interface between the sea and the atmosphere. The sea tends to slow down the ocean, and it slows down in the ocean within the Ekman layer in the atmosphere. So we have both atmospheric and oceanic Ekman layer. In one, the atmosphere influences the ocean, trying to accelerate the sea surface, the sea water. In another, in the atmosphere, Ekman layer in the atmosphere, is close to the interface ocean atmosphere, and tries to slow down the movement of the atmosphere. Indeed, when you measure the wind over in the atmosphere, you find out very easily that both about the sea and about the land surface, the wind speed increases very quickly from the height from the sea surface or land surface with height. Because why? Because of the friction. The friction is trying to reduce the velocity between the two fluids, or between the land surface and the atmosphere. And this makes this strong changes of the velocity with depth or with height in the atmosphere or in the ocean, respectively. The surface drifters, which are, if you remember, are the bodies which you put into the sea, and they simply are drifted by currents. They tend to drift parallel to lines of constant atmospheric pressure at the sea surface. Why? Constant atmospheric pressure, the lines of constant atmospheric pressure, according to the geostrophic approximation, are also the lines of the wind, or are the lines along which the wind is blowing. But due to the friction, this is not a purely geostrophic wind, but it's slightly turned to the right. And so, consistent with Eggman theory, which we will be now looking at, the drifters are moving parallel to constant atmospheric pressure lines at the sea surface, which is something which is exactly what we'll see later on from Eggman theory. The flow average over many inertial periods is almost exactly that calculated from Equine theory. This is what is something what we will be looking at. Now we will let's see another important concepts of the response of the wind to winds in the atmosphere. The transport of the generated by the wind is 90 degrees to the right of the wind in the northern hemisphere. So, at the very thin surface layer, the flow is 45 degrees with respect to the wind direction, looking downward to the right-hand side. If you consider the transport is something else. The transport is the integral of the water transported from the wind-induced current from the surface to the depth where you don't feel anymore the influence of the wind. And this transport or water transport is 90 degrees to the right of the wind in the northern hemisphere. So these are the two important things. One is the surface current, steady wind generated current, which is 45 degrees to the right-hand side of the wind in the northern hemisphere, looking downwind. Transport is, on the other hand, water transport in the surface Ekman layer is at 90 degrees to the right-hand side of the wind in the northern hemisphere. So these are these two important concepts. It seems at the first sight, it will seem strange that the wind, which is blowing in one direction, generates the transport to the right-hand side with respect to its direction. But you will see it later on from the equation that this comes from. The first empirical evidences of this fact that the surface flow is 45 degrees with respect to the wind direction has been noticed in the polar areas. In the northern pole, you know that there are icebergs or pieces of ice which are floating around in the polar areas, and you know also that you probably know that the icebergs are only 10% outside of the ocean, and 90% are below the ocean surface. And what people were noticed while being there, they noticed that if you have the wind, they were noticing the wind blowing in one direction, while the icebergs didn't follow the wind direction. They simply went in a direction more or less about 90 degrees with respect to the wind direction. And obviously, this can be also explained in terms of the fact that most of the surface on which acts the currents to icebergs is below the sea surface. Therefore, the movement of the icebergs do not reflect what is happening above the sea surface. They don't react to the influence of the wind, but they do react on what is happening below the sea surface. Below the sea surface, what is feeling the movement or the current movement is this large surface and part of the iceberg below the sea surface, and therefore they notice that this is about 90 degrees to the right of the wind. This is an first empirical evidences that the influence of the wind manifests in such a way. We will see now very soon the solution of this. Another aspect of the response to the wind, important concept, is that the spatial variability of Ekman transport. So Ekman transport depends on the wind, and due to the variability of the wind over distances of hundreds of kilometers and days, leads to convergence or divergence of the transport. So if you have different Ekman transport in different parts of the world, due to this concept that transport is 90 degrees to the right of the wind direction, there will be a convergence or divergence in different parts of the oceans, and because the transport will converge or diverge due to these. We have winds blowing toward the equator along the west coast of continents. Okay, what is this? If we have the wind blowing toward the equator along the west coast of can you imagine the west coast of the continent? And if it goes toward the equator, due to the fact that the transport is 90 degrees to the right of the wind in the northern hemisphere, the transport will be surface transport or wind-induced transport will be from the coast toward the open sea. Okay? So we will be losing the surface mass along the continent, along the coast. But then this will, since you have to have the continuity of mass of water, you cannot have a loss of water from near the coast and having the hole there. You have to have somehow the compensatory current from deeper layers toward the coast. So what you are getting near the coast is that at the surface you have the Ekman transport from the coast to the open sea, while this leads then to the transport from the coast, from the open sea toward the coast in deeper layers. But then within about 100 kilometers from the shore, there will be the vertical motion from deeper layer to the surface. And this is what we call upwelling. Upwelling means that this upward motion of the water near the coast, near the continent coast, due to the Ekman transport, which is perpendicular to the coast and in seaward, and this is due to the equatorward wind blowing along west coast of the continents. This is very important thing. What we will be talking a lot is this the phenomenon upwelling, because this upwelling phenomena, for example, you have heard also about El Nino, but we will be just mentioning this here, and you will have more chances to hear in a continuation of the course. What is important aspect of these of this influence of wind in the coastal areas, which creates the upwelling, is that the upwelled water is, on one hand, is colder, so that means that it modifies the weather along the west coast. Modifies the weather in the sense that the ocean is cooler than it is in a situation without the wind. This is one thing. So you have since the ocean is cooler, then you have the influence on the climate is important. This is one thing. But the other thing, which is also extremely important, is that if you bring the deeper layer water into the surface, you're bringing nutrients. The nutrients which are deep in the ocean, they exist there. They are in very high concentration, because the phytoplankton biomass in deeper layers where there is no light, it's very low, and therefore nutrients remain there in high concentration. There is now no organism which will consume them. And therefore, you're bringing these nutrients into the surface there, into the layer where the lights is strong enough to enable phytoplankton to grow. But phytoplankton cannot grow only due to the light availability. It should grow also due to the availability of nutrients. Therefore, by bringing the nutrients into the upwelling areas, you're bringing the nutrients into the surface layer, making it available to phytoplankton, which has, in that case, it has enough light available and has enough nutrient available, and therefore in the upwelling areas, they are usually rich in phytoplankton. But being rich in phytoplankton it's not the only aspect. The other aspect, very important, is that there is what we call nutritional chain, where the phytoplankton is eaten by zooplankton, and zooplankton is eaten by fish. So once you get the enough nutrients that the phytoplankton starts to bloom, the marine plants start blooming, you will immediately get the zooplankton, which starts eating the phytoplankton, And so you have the increase of biomass of phytoplankton, increase as a consequence, increase of phytoplankton, of biomass of zooplankton, and then finally, as the end of this chain, there is a fish. The fish starts to grow because it has enough food. Therefore, as a consequence of this, the upwelling areas are rich in the fishery, in the fishing, and these are typically fishing grounds. And this is why the upwelling is a very strong, very important. Upwelling areas are very important from the economical point of view. These are usually fishing grounds, rich fishing grounds where the fishery takes place. Intensive fishery takes place, which is good or not bad. Which is both good and bad, because fishing too much is not good. But anyhow, that's another question. What we want to be treating here. Economically and historically, these areas are very, very important. And then finally, we have something which is called Ekman Pumping. Ekman Pumping means that the spatial variability of Ekman Transport over distances of hundreds of kilometers leads to convergence and divergence of the transport. If you have a convergence of the transport in the Eggman layer, what happens? Convergence. If you have a convergence, then you automatically produce the vertical movement from the surface to deeper layers, because otherwise you would have the accumulation of water in a certain place, but you cannot have accumulation of water. You can have bumps at the sea surface, or at least not the big bumps. So you create the vertical movement downwind, down in the deeper layers. If you have, on the other hand, if you have divergence in the Equine layer, or such spatial variability of winds over distances of hundreds of kilometers, if you have a divergence, then this recalls the water from deeper layers into the surface layer, and you got the upwelling. So you can get the upwelling at the open sea, not only along the coast, because there is certain divergence in the surface layer due to the divergent Ekman transport, and this due to the spatial variability of this Ekman transport. So you have, and this process where you get the vertical pumping or sucking the water from deeper layers. This is called the Ekman pumping. So the pumping of the water due to the divergence or convergence of the Ekman transport, which is on its side associated with spatial variability of winds. Okay, so these are important concepts. What we will be talking about. These are the points we will be talking about. We have the Ekman layer, the sea surface, which I already mentioned, and this Ekman layer at the sea surface, as we know, as we have said in advance, that this is between 40 and 400 meters, several hundred meters. We have the Ekman mass transport due to the whatever is happening in the Ekman layer, and we have the application of Ekman theory. Application of Ekman theory are these two aspects, what I just mentioned before, is the coastal upwelling, we have equatorial upwelling, we have Ekman pumping, but here, which is not mentioned here, is the open ocean upwelling, because open ocean upwelling is also another not necessarily related to the equatorial upwelling. Although I must say that the open ocean upwelling is not so important as, for example, coastal upwelling or equatorial upwelling, because the open ocean upwelling is associated with the heterogeneity of the wind field at the open ocean, which is typically not very strong. The ocean wind over the ocean is rather smoothly distributed over space, and therefore the open ocean upwelling is typically not as strong as equatorial upwelling or coastal upwelling. In the coastal upwelling, we are talking about the layer near the belt near the coast, about 100 kilometer wide. By the open ocean, the upwelling is on a spatial scale on the order of 1,000 kilometers. Equatorial upwelling is also on a smaller scale, and you will see how it works. And then finally, we have Eggman Pumping, what I already mentioned. Now let's I will not go into very much details to these equations, but we should we should mention these, and I want when talking about this, I will not ask you details about that. I will try to I'm talking about the exam. I will ask you the concepts. I will ask you whether you understood the physical aspects. I want to ask you a lot about the mathematical formalism. I don't know how and to what extent other teachers of this very course you will find out with them. But what for me, what is important and what is important for this part of the course is that you get the idea of what is the physics of the processes in the ocean, not necessarily being supported by the mathematical formalism, but some of the mathematical formalism we should consider. You remember when we were talking about the solution, geostrophic solution of the equation solution, what are the most important assumptions of the equation of motion for the geostrophic flow? One is that we assume the steady state, so there is no time dependence of the solution. The other assumption is that there are no non-linearity in the equations of motion. So the advection is zero. The third thing is that we have the only force is pressure gradient force. So we have in the case of the geostrophic flow, we have inertial motion. We have the motion which is generated by the pressure difference and Coriolis. And this is steady state solution. Now, if you go to the Ekman transport, to the Ekman solution, in the Ekman solution, we again assume the steady state. So the Ekman solution is the steady solution of the equations of motion. So there is no parts which represent the derivative of the velocities with time. There is we neglect the nonlinear part. We are then left on the left-hand side only with the Coriolis force. And on the other side of the equation, we have the only thing what we have is friction. We neglect the horizontal pressure gradient. Therefore, we have again only two terms. We have the Coriolis force, and we have the frictional forces. So, on one hand, if you think of the geostrophic solutions, you have the balance between the Coriolis force and the friction and pressure gradient force. On the other hand, in the Ekman layer solution, we have the balance between the Coriolis force and the wind stress and the frictional part. Therefore, both solutions are time independent, are steady solutions, and there is no time dependent in it. Sorry. So that means that these solutions are good approximation in the case the current field or the forcing in this specific case doesn't change fastly on doesn't have a time scale, short time scales. And because for a short time scales, if you remember, we have to keep the time-dependent term, and for example, as an inertial oscillations. So in both cases, geostrophic and Ekman solution, we have the steady state solution, and they are valid for certain time scales longer than like in a geostrophic flow, longer than the time scale on the order of few tens of days, 10, 20, or 100, even 100 days, and spatial scales on the order of 100 kilometers, 10 to 100 kilometers. And similar thing is valid for the Eggman layer. So what we are left with, these are these two equations. All these equations of motion are reduced to these the two equations with two unknowns in x and y direction. And obviously, again, f is Coriolis parameter. Az is the frictional constant, and du dz, and we approximate the friction with this kind of term. So we have the frictional term is proportional to the vertical gradient of velocities, to the vertical shear. And so when we put these into the equation, we obtain this kind of equation. And now with the it is easy to verify that these equations, this thing here, have these two kind of solutions, which is where we have a V0 exponent to AZ and multiplied by cosine or sine. What that means? That means that the solution of this kind of equation is the U and V component, which are decaying exponentially from surface to deeper layers on one hand, and on the other hand, there is also the rotation of these components, or the velocity with depth going downward. So the magnitude of these velocities is reducing exponentially, while it turns in the anti-clockwise direction from the surface to deeper layers. Here we obtain the constants for the case where the wind is blowing to the north, and we obtain this thing here. And so these are the solution, and but in order to get the solution, we have to define we have to define also the boundary conditions. And one of the first boundary condition at the z equals 0 at the surface is that the velocities are 45 degrees with respect to the wind, and to the right-hand side of the wind at the sea surface. Absolute. That's associated to this thing. If you put here a z equals 0, you obtain this boundary condition at the sea surface, and this is how we already underline in the important concepts that the current has a speed v0 at the northeast, and in general the surface current is 45 degrees to the right of the wind when looking down in the northern hemisphere. This means, these two equations mean that. In the southern hemisphere, obviously, it is opposite. Below the surface, the velocity decays exponentially with depth. From this equation here, from this solution here, we obtain that the amplitude or the velocity magnitude decrease exponentially with depth. And this equation says that. So you start with the equation, you start with the velocity, which is V0 at the sea surface to the right-hand side of the wind direction, and then going deeper and deeper, its magnitude decrease is exponentially going down into deep. So let's see under which conditions the Ekman has obtained these solutions. By seeing under which conditions the Ekman obtained these solutions, we can also understand in which conditions and how good and in which conditions are valid or good assumptions of the real wind-induced flow in the ocean. First assumption is that there are no boundaries. So this kind of solution is valid away from coasts. No boundaries, because boundary would complicate, boundaries will introduce the lateral friction, and therefore there will be not the prevalence only the vertical friction, but also the lateral friction, which then certainly will not result in this kind of solution. We have to have a deep water. This means that it's valid for the water if depth is larger, much larger than 200 meters. Why deep waters? Because you remember at the very beginning of our course, we said that at the surface and at the bottom, we have what we call the frictional layer, the layer where we feel the friction. At the surface layer, this is the Ekman layer, where there is a friction acting between the ocean and the atmosphere. But the same thing is, or similar or equivalent thing happens in a bottom layer, where there is a large differences in the velocity between the water and the bottom, which stays steady, stays there, doesn't move. So in the deep layer, we have also the Eggman layer. Therefore, and if we have a very shallow water, we will have the superposition of the two Eggman layers, the surface Eggman layer and deeper Eggman layer. And therefore, this solution for the wind influence of the sea surface will not be reflecting the fact what is happening in the ocean. So in order to avoid the superposition of the surface and Eggman layer, we have to have the depth larger than 200 meter depth. Then we have to have the F-plane. We have to have that F is constant. So this, what that means F-plane? Means that the F, the Coriolis parameter, doesn't change too much with the particle. So that means that the particle will not be moving north, south in large distances in order that we have to take into consideration the change of the F. So this is the F-plane approximation. And so that means that this kind of solution is valid for the movement, north-south movement on the order between 100 and 1,000 kilometers. And this is something that we have to keep in mind. Okay, we cannot get the Eggman layer solution if we move from 45 to 80 degrees north. The fourth assumption is a steady state. As I told you before, the steady state is valid if the wind blows for longer than a pendulum day. Pendulum day is this inertial period, which is on the order of 1 day or 17 hours, 1 day, and so forth. So the steady state solution or the Eggman layer solution is valid if the wind doesn't change for in a period shorter than about a day. The similar thing is, if you remember, The similar assumptions are valid for the geostrophic flow. Here is the next assumption is that AZ is a function of U10. I won't go into much details. And then finally, it's homogeneous density. This is probably good if except as it affects stability. So the homogeneous density means that the density doesn't change too much with depth. This is also not bad as a assumption, because if you consider that the density changes very fast, very strongly in a very thin surface layer. We have seen in one of our previous slides that the density changes very strongly due to the seasonal heating and cooling in the first 50 meters. And this is a relatively thin surface layer, which allows us to assume the homogeneous density with respect to 400 meters. What is the typical depth of the Ekman layer? Okay. So now let's see the Ekman transport. The Ekman transport, what we have said in advance that it is to the right-hand side with respect to the wind direction. And we will obtain this by integrating the equations, the equations of motion, by integrating the solutions of the Ekman solution with depth. In that case, we will obtain the amount of mass which is transported in the Ekman layer, obviously multiplied by rho, by the density of seawater, and that's what we obtain the transport, which has a unit of kilogram per meter per meter per second. And so we integrate the Ekman transport, integrate the solutions of the Ekman solution from the surface to the minus d. D is the depth of the Eggman layer depth. But we will see later on how we get this Eggman layer depth. So we do this integration over x and y direction using the x and y velocity components, and we calculate the Eggman mass transport by integrating these things, and so we obtain this that the Eggman mass transport is proportional to the friction at the surface and the friction at the z in dp of the ocean. A few hundred meters below the surface, the Eggman velocities approach to zero. They approach to zero because they usually, as you said before, we don't feel the impact of the wind. So the last term, this term here, is therefore zero because here the friction is zero. So we end up with this thing equal the friction at the surface. And so we have the transport in the y direction. The Eggman transport in the y direction is proportional to the friction at the x direction, and vice versa. The transport in the x direction is proportional to the stress in the y direction. So we calculate these are the results of that. These are the two components of the stress at the sea surface, and these are the two components of the transport. You can see that these two are directly proportional to the wind stress. And again, from here, you can notice from here that the transport is perpendicular to the wind stress. And this is to the right of the wind in the northern hemisphere. These two equations combining says simply that the transport is perpendicular to the wind stress and to the right of the wind in the northern hemisphere. This is what what I told you in advance at the very beginning as one of the important concepts of the influence. If wind is to the north in the positive y direction, to the north, in the positive y direction, the south wind, then Tx6 is equal to 0, and transport in the y direction is 0. So we have the x transport. The x transport, which is transport toward east, is proportional to the frictional force toward north. So in the northern hemisphere, the F is positive and the transport is in the x direction to the east. So if we go, so if our wind is northward, okay, the F is positive because we are the northern hemisphere. The mass transport is that in the x direction. We said x direction is positive toward east, and therefore we have the wind blowing northward, and the Ekman max transport is to the right. That means to the east. As we said before, it may seem strange that the drag of the wind or the water leads to current at right angles to the drag. The results, in fact, follows from the assumption that the friction is confined in a thin surface boundary layer, and that it is zero in the interior of the ocean, and that the currents are in equilibrium with the wind, so that there is no longer acceleration, no longer accelerating. There is no acceleration, and these are in steady state equilibrium. And due to this assumption, the transport is to the right hand side with respect to the wind. So this surprising feature, if we may say, is due to simply to the assumption we enter into the equation and then we obtain the solutions. Okay, let's see how it looks like in a 3D representation, so that it might be, I hope, might be more clear what we see. So let's see how it looks like. This is the vertical axis, z-axis. This is the surface, sea surface. Wind direction is this way, okay? Already at the sea surface, the current is 45 degrees with respect to the wind. And if we have the wind direction like it's a 2% of this thing here, so we have the, like, if you assume that this is 6.4 centimeters per second, I don't know where this is generated by 10-meter wind at 35 degrees north, and so a certain percentage of this wind speed is the flow. So if this is 10 meters per second, this is that's few percentage, so we have a 6.4 centimeters per second back to the right hand side, 45 degrees with respect to the wind direction in the northern hemisphere. When we go deeper and deeper, what is happening? The velocity, the magnitude of these vectors reduces exponentially. The magnitude reduces exponentially, becomes smaller and smaller as an exponent of z, and so these are the projection of these horizontal current speed, and you can see that it reduces exponentially as magnitude, but at the same time it turns clockwise direction with depth and so at a certain depth, the current which is generated by the wind becomes exactly the opposite direction with respect to the surface, with respect to the surface current, with respect to the wind field. So this is how we. So that's also another the first look paradox where the wind flow, the wind current, wind induced currents are in the opposite direction at a certain depth with respect to the wind. And according to some arbitrary definition, the wind, the Ekman layer is defined at a depth where the current is in the direction opposite with the direction of the wind. So this is how it looks like. This is, I think, I find this this illustration very nice because it gives you the idea how this looks like in the ocean. If we integrate these all these equations, what we have done by trying to estimate the Ekman transport, then we will obtain the Ekman transport to the right-hand side with respect to the wind. And so this is practically integral from the surface to the bottom, from the surface to the bottom of the Ekman layer, multiplied by rho, by the density of the water, and integrated from the surface to the certain layer. Since the density is considered constant, we can take it outside of the integral and integrate simply the velocity. We have one important number, non-dimensional number, which gives us the possibility to estimate whether and to what extent we can assume that the equations of motion can be reduced to the Ekman type of equations. And this number, this non-dimensional number, is obtained as a ratio between the frictional force and the Coriolis force. So this is the Ekman number. So if this Ekman number is very small, then we can assume that if this Ekman number is on the order of 1, we can assume the Ekman equilibrium. We can start looking, or we can say, yes, the Ekman solution describes well our motion. And this is this Ekman number, which is the ratio between the frictional coefficient, Coriolis parameter, and the depth of the Ekman layer depth. Ekman layer depth is the thickness of the Ekman layer. It's arbitrary, as I told you before, because the Ekman currents decreases exponentially with depth. So the Ekman proposed that the thickness be the depth at which the current is opposite, as I told you before, the velocity at the surface, which occurs at the depth of dE, the Ekman layer depth, and which is defined as this thing here. This is so the Ekman layer depth is proportional to the friction on one hand, and on the other hand is inversely proportional to the Coriolis parameter. What says this? This says that the stronger is the differences in vertical gradient of velocity between the wind and the ocean, the deeper is the Ekman layer. It's something what we would expect also empirically. On the other hand, the Ekman layer depth is larger if you are closer to the equator. So the closer to the equator is, with the same velocity with the same differences of velocity between the surface, with the atmosphere and the ocean, with the same differences in velocity, if we are closer to the equator, the deeper is the Ekman layer. Okay? There is another thing interesting here. That at the equator, the Ekman layer depth is not defined because you have this divided by 0, which is undefined number. Therefore, at the very equator, the Ekman layer is not defined. So you have this is only also because this is also, if you look at the if you look at the solution in the northern hemisphere, the Ekman transport is to the right hand side of the wind with respect to the wind direction. If you cross the equator, go to the south, the Ekman transport is to the left-hand side with respect to the wind. So the same direction of the wind on the north and on the south of the equator generates the divergent transport, Ekman transport. So in the northern hemisphere, with the same direction of the wind, you have the transport northward, and if you cross the equator to the southern part of the equator, the Ekman transport is to the south. So this is what I mentioned. This is what we mentioned on one of the upwelling. One is the upwelling is, for example, the equatorial upwelling. Equatorial upwelling is due simply to the fact that we change the sign of the Coriolis parameter. Although the wind is of the same direction, we have so-called equatorial winds, which are in the same direction, both north and to the south of the equator. But the same direction of the wind generates the flow from the equator toward north and from the equator towards south. So the same direction of wind generates the divergence at the equator and the upwelling. So there is an upwelling, equatorial upwelling, due to the changes, simply due to the changes of the sign of the Coriolis parameter and due to the changes of the direction of the Eggman layer transport. So using this equation here, and with typical winds of 10 meters per second, as I told you before, Eggman layer depth varies between 45 and 300 meters in function of the sign, in function of the Coriolis parameter. And the velocity of the surface current varies from 2.5 to 1.1% of the wind speed, depending obviously on latitude. And these are the typical Ekman layer depths at 15 and 45 degrees for different wind speed. One is for 5 meters, 75, 45, 150, 90, 300, 880. So you can see that that as we already seen from the equations, from the solutions, that the Ekman layer depth depends on the wind speed on one hand, and on the other hand, it depends on the latitude. The more to the north you are, the smaller is the Ekman layer depth, or the closer to the equator is, the larger is the Ekman depth. Now we come up to something which is called the Equine pumping, which I already mentioned to you, is that the horizontal variability of the wind blowing over the sea surface leads to horizontal variability of the Eggman transport. Because we have seen that the Eggman transport is proportional. Eggman transport, which is here, Eggman transport is proportional to the friction. Okay, and the friction is this thing here. So here we are. Sorry. So the wind blowing on the sea surface leads to horizontal variability of the Ekman transport. And because of the fact that the mass of the seawater should be conserved, must be conserved, the spatial variability of transport must lead to vertical velocities at the top of the Ekman layer. As I told you before, if we have the divergence, if we have the flow flowing from one point to one side and to the other side, we have a divergence, and we create the vertical velocity toward the sea surface, and vice versa. If we have a convergence, then we have the vertical velocity toward the deeper layers due to this heterogeneity of the wind. To calculate this velocity, this vertical velocity, we have therefore to integrate the continuity equation. We have to, the continuity equation says that there is no water mass lost or gained, and therefore, if we integrate the water mass, the continuity equation from 0 to the bottom of the Eggman layer, this has to be 0. We cannot lose or gain the water mass. Therefore, this thing here is here, and now we do some little manipulation of this thing, and we obtain that the dMEx, the Eggman layer transport in the x direction, derivative of the Eggman layer transport in the x direction, plus derivative of the Eggman layer transport in y direction is equal to vertical velocity at the surface and vertical velocity at the bottom of at the base of the Eggman layer. At the surface, the vertical velocity at the Eggman layer, at the base of the Eggman layer, must be 0, because we cannot have the flow through the Eggman layer at the base. We have to have the velocities within the Eggman layer. Therefore, if by looking at this equation here, we obtain that the Eggman layer divergence. This is the divergence of the Eggman layer. So we are calculating to what extent the water in the Eggman layer has been taken away from one place to another. Creates the vertical velocity. This is exactly what we have said. If we have the divergence, so if we have the dm, this part left-hand side, if it's positive, then we have the vertical velocity negative, it means downward, and vice versa. Therefore, the vertical velocity, the vertical movement are compensating for the loss of mass within the Eggman layer due to the Eggman layer divergence or convergence. So that's another way of formulating this in terms of the mathematical formalism. So this equation really states that the horizontal divergence of the Eggman transport leads to vertical velocity. There is no vertical velocity if we don't have the divergence of the Eggman transport. Okay, and so this process, as I mentioned before, is called the Eggman pumping. The Eggman pumping means simply the vertical velocities generated by the divergence in the Eggman layer. And we can connect these Eggman mass transport, and we can connect this Eggman pumping to the wind stress. So what we obtain finally is this thing here. What has this thing here? This thing here, we have that the Eggman, the vertical velocity is associated to the Eggman layer divergence. But then we succeeded to connect this Ekman layer divergence to the whatever is happening in the wind field. Therefore, the curl curl of the wind stress. So that means the spatial heterogeneity of the wind field generates the vertical velocity. First generates the divergence and then generates the vertical velocity. So these two equations, this one and this one, are strictly connected to each other. If we have the spatial variability of the wind field, there is, as a consequence, there is of that is the horizontal divergence of the mass in the Eggman layer, and as a consequence of that, we have the vertical velocities up or down. Okay, so that's a very important aspect of the influence of the wind on the distribution of mass. So that's simply egg pumping in the ocean. So the vertical velocity in the Eggman layer at the surface is proportional to the wind stress curve, and this is essential equation which determines the upwelling or downwelling. But then you will see later on that this determines also the vorticity field. And it determines the stretching or squeezing of the water column. But what means the vertical velocity being positive or negative? It means that or you are squeezing the water column because the vertical velocity is upward, or you are stretching the water column and the velocity is downward. And you can see here that this vertical velocity of stretching or squeezing of the water column can be generated by the curl of the wind stress. Okay, so coming back to if you remember let me come back to this thing here. Okay, this thing here, this graph here. Here, this graph here, we said before that there is no, in the case, there should be external force which makes this water column changing its height. Otherwise, the water column will not go from here to here without any external force. You cannot force the water column going from here to there unless you apply some external force. One of the external forces which changes the water column height is the heterogeneity of the wind field, spatial variability of the wind field. Spatial variability of the wind field creates the vertical velocity, inducing the stretching of the water column, and then making this water column longer, deeper, and creating additional relative vorticity of the water column. So we can generate the relative vorticity of the water column due to the spatial variability of the wind field. And we can cause the faster spin of the water column simply due to the spatial variability of the wind field. So that's just to give you an idea how what is the importance of this spatial variability of the wind field. I think we should stop here, and because from these basic concepts and basic equations, which gives us the and basic assumptions, what gives us the Ekman layer solution, we can go on and consider and try to interpret the global ocean circulation in terms of the influence of the wind. Because you remember before, we tried to interpret the global ocean circulation, the global conveyor belt in terms of the differences in temperature and salinity between equatorial and polar areas, and what we call a global conveyor belt. Now we will try to describe or interpret the global conveyor belt, the global ocean circulation in terms of the wind influence. And you will see that these two forcing are superimposing one on each other, and they are creating essentially the same type of circulation. So and finally, you are not able to distinguish what is the wind-driven circulation from what is the thermohaline circulation, except of the fact that, as we mentioned before, that the wind influence is felt at the first 1,000 meters in the ocean, while the thermohaline differences or differences in temperature and salinity and in density and in horizontal pressure gradient are felt in the entire water column, and the influence of the horizontal pressure gradient is felt in the deeper part of the ocean, in the ocean below these 1,000 meters of what we call, between 1,000 and 5,000 meters. This is what we call the interior ocean, the interior part of the ocean, where the geostrophic approximation is a very good approximation. If we go to the surface layer, if we go the first 1,000 meters, where do we feel the influence of the wind? There we have the best approximation is the Eggman solution. So we have, and this is the surface frictional, surface Ekman layer, where the Eggman solution prevails, and we have an interior part of the ocean where the geostrophic flow or geostrophic assumption prevails. So this is how we can vertically distinguish two parts of the world ocean in terms of the physics, in terms of the physical approximations, which are the best approximation for the water, for currents and flow. Okay, that's it. I think I will stop here, and I don't have anything to say except have a good time. I repeat again, whatever kind of questions regarding this thing, please write to me and tell me any type of your impressions or questions or whatever. You just write me and I'll try to answer. And I haven't had time to share with you PowerPoint. I hope I will do it these days. Okay, thank you. Bye-bye.
Bye. Bye.
Bye. Thank you.
Bye.
Thank you. Bye.